All right, as you are introducing yourselves in the chat box, we wanted to say welcome, or I wanted to say welcome. Hi, everyone. I'm Tiffany Neal. I serve as the Curriculum Innovations Manager at OpenSciEd, and I'm thrilled to be joined by two of our curriculum developers for this project and many others. We have Michael Novak and Nicole Vick, who are both from Northwestern University from the Storyline team, and they actually were part of the development team that worked on this unit that we're excited to share more with you about today, the 8.2 Sound plus Computer Science unit. So as we move along in the webinar today, we'll have various points where we're going to ask you to engage in the chat box, and hopefully we'll get some opportunities for you to experience what students might experience in this particular unit. So just a quick snapshot of what we'll cover in our time together. We're going to talk a little bit about the rationale behind the OpenSciEd plus computer science integrated effort. We're also going to walk through the storyline of this unit, 8.2 Sound plus Computer Science. And if storyline is a new phrase for you, don't worry, we'll go over that in our time together today as well. Just know that we're going to really walk through every aspect of this unit and give you a sense of what students will experience as they move along in their learning through the unit. And as I mentioned, we're going to experience part of the unit itself. And so if you're interested to see how computer science actually comes to life in these units, you'll get to experience that today with us. We're also excited to share some new features we've built into these units to better support you with providing instruction to students. And we'll leave a little time at the end for question and answer. So that's how we'll spend our time together today. Also, some of you may be familiar with OpenSciEd, but if you're not, we want to welcome you and just give you an overview of what we do here at OpenSciEd. So we are a nonprofit organization, and we work with curriculum developers, state science administrators, educators, and philanthropic organizations to develop free, high-quality instructional materials and professional learning. So we're going to dive in just a little bit to a little more information about our effort to integrate computer science into a few of our OpenSciEd middle school science units. So in undertaking this effort, we decided to focus on 5 units across the middle school science curriculum for OpenSciEd. We have 2 6th grade units, 1 7th grade unit, and 2 8th grade units that we have redesigned with the help of our wonderful partners at Northwestern. And what you should know about the redesign of these units is, one, if you're familiar with the units, we held on to the anchoring phenomenon. So that phenomenon that really anchors the full unit and learning experience for students. That anchor does not change in the redesign for the computer science units. We also maintain the same alignment for each of these units to the original next generation science standards that the units were aligned to. But we have now worked to infuse computer science in such a way where if students experience all 5 of these units over the course of their middle school experience, they will have covered or experienced a little over 80% of the Computer Science Teachers Association standards for computer science learning. And somehow we were able to do all of this and ensure that the units are not any longer in length and instructional days than the original units. So there's a lot packed into the units. However, they've been redesigned for what we think of as efficiency. So same anchoring phenomenon, same alignment to next generation science standards, addition of computer science standards and learning, all in the same time frame. And if you're wondering how we did that, we'll share more about that today. We also wanted to highlight our partners in the work. So we want to first acknowledge and thank Amazon Future Engineer, who is our philanthropic sponsor for this work. And they have been wonderful partners in helping us also identify some people in the field of computer science that can bring to life some aspects of our units as well. We also partnered with the Center to Support Excellence in Teaching from Stanford University for all of our professional learning for the project. And I already mentioned the wonderful group at Northwestern, the Next Gen Storyline Group, and Horizon Research Inc., who collected all of our data during our field testing of the computer science units. And just like the original OpenSciEd science units, we did field test the computer science units with educators and students across the nation. So last year, we field tested the units in 5 states with around 76 teachers and a little over 8,000 students. Um, and if you are familiar with the process we use at OpenSciEd to develop units, this may look familiar to you, but we really spend about 9 months developing a unit from the initial writing phase to field testing. And then we spend a lot of time getting feedback from teachers and students who experience the units in refining them before we publish them for final release. So that's how we got to the point today where we're excited to share with you the 8.2 unit. Also, if you are less familiar with OpenSciEd, and this may be your first time being introduced to our instructional model, I want to share a little bit about this instructional model with which the units are really designed around. So just like the original OpenSciEd middle school science units, the CS integrated units follow this instructional model. That really is based around what we call the storyline approach, where we start with an anchoring phenomenon or problem, and students work through a series of investigations designed to help them figure out how the science, and now the computer science, explains the phenomenon or helps them answer a problem. Oh, I think we may have to. I bet we got it taken care of. I bet we got the muting taken care of. So in addition to opportunities to engage in investigations, students get a chance through this instructional model to engage in things like putting pieces together in the lessons, in some routines that we call the navigation routine. And really the purpose of this instructional model is to really help students move from starting to investigate the anchoring phenomenon to collecting more and more information throughout or data or understanding throughout the unit so that they can answer or explain that phenomenon or develop a solution to the problem. So that's our instructional model. And you'll note with the computer science integrated units, and we'll go into this in a little more depth in a moment, but the computer science aspects are actually woven throughout the unit. So we don't wait until the end to integrate computer science. We don't integrate computer science in one spot in the unit. It really is thoughtfully threaded throughout the unit. So one thing we wanted to take a moment to explore is why OpenSciEd is undertaking this effort of integrating computer science. Well, we are hoping to expand access to computer science learning for all students. As some of you may know, right now, some students do have access to computer science in middle school, while others do not, because it's often offered as an optional or elective course. So we hope to expand student access to computer science by integrating it into the OpenSciEd science units. And we hope to provide students with an authentic STEM integrated learning experience or experiences. We did create the integrated units also to deepen both science and computer science learning, and to support schools and districts with new pathways for meeting computer science policy demands. We know many states and school districts are now requiring computer science at the middle school level, so we hope this will support them in meeting those policy demands. And finally, we hope that the units provide students with an opportunity to shift their perspectives on the role computer science can play in their lives. So with that being said, we want to take a moment to engage you in the chat box. We know that you showed up today because there's some interest in the OpenSciEd computer science units, but we'd love to hear from you if you don't mind. What excites you about integrating science and computer science? And we'd also love just some ways that you may be already thinking about how this looks in the classroom. Um, if you've desired to see a classroom with computer science integration, what do you hope that looks like? Or maybe you've seen integration yourself. So tell us what excites you and what this type of integration might look like, computer science and science in the classroom. And Michael and Nicole, I will ask that you help share some of those ideas from the chat box if you don't mind, as folks are sharing them. We'll give it just a couple of minutes for this. What excites you about integrating science and computer science, that idea? Or what do you think it could look like in the classroom? All right. Michael, Nicole, any ideas popping up that we can share?
Absolutely.
Yes.
Nicole, you want to share the first couple?
Oh, sure. So, Roz is in Washington State and shared that she wants to increase student interest. And then Nicole, who also has an amazing name, is excited to strengthen student data collection and accuracy, so that the pre-existing equipment is less of a black box. And Michael?
I see another post from Amanda where she's had some experiences teaching with microbits, in robotics in particular, but as an elective, right? But now the STEM program's cut from the school and wants a more reliable way to make sure that we're getting CS into kids' classes. So some CS in eighth grade with her is going to be the opportunity that she makes available to all kids this year, maybe.
Wonderful. Well, I think we're on the right track with how we've structured the units and the webinar today. So hopefully we'll see a lot of connection between what folks are excited about or hopeful for and how the units play out. We have asked educators this very question, or the second question that we were reflecting on: what has computer science and science integration looked like in the classroom? And these are some of the ideas that have been shared with us in the past. Things like use of spreadsheets or computer programs to analyze data. We've also seen the use of like scientific probeware to collect data. For some teachers, they see computer science and science integration as incorporating a day of code into the science classroom. Maybe even some folks engaging in game development in their classrooms, considering real world context. So whereby perhaps if they're developing a game system based on the real world, they're having to think about a lot of life science concepts or maybe earth and space science concepts to build out that world. Or computer programs being used to present findings or share ideas. We wanted to give you an idea of some of those examples while also showing what we have done with our effort to integrate computer science and science. So in the OpenSciEd plus computer science units, as I mentioned, computer science is going to be threaded throughout. Here on the screen, you'll see an example of the 8.2 Sound plus Computer Science unit. And these are all of the 14 lessons that are available in this unit. And the little icons that you see that do have a connection to coding, which we'll talk about later, represent all of the spaces in this unit where computer science is integrated. And students are using computer science at these points and various points in the unit to engage in things like data analysis or designing algorithms. They may be developing or using technology to further their understanding of a phenomenon or to solve a problem. Um, but really, our goal is to make sure that the computer science that is integrated or leveraged by students really allows them to experience computer science as a powerful tool for sense making. And just a little more insights into our thinking about the role computer science plays in these units. We really believe by integrating computer science, students get a chance to engage in rich, meaningful STEM experiences or STEM integration experiences. So on the left, you're going to see 4 of the 5 core computer science concepts from the Computer Science Teacher Association standards. These closely align with the goals and practices of the 4 STEM disciplines. So, for example, computer science connects with science through things like data analysis and systems thinking, which are core in GSS components. It supports engineering through things like designing and testing solutions, and connects to technology through purposeful use and creation of technology through computer science. And finally, mathematical practices show up through things like algorithms, patterns recognition, and modeling. So when we talk about integrating computer science, we're really leveraging the natural overlap between computer science and the broader STEM disciplines. Whether students are collecting sensor data, coding, or evaluating technological impacts, computer science becomes just a part of how they do science and solve problems. We actually think of STEM integration in these units more like the way that we might think about a soundboard. So a soundboard, like the image we see here, where each of the four disciplines is turned all the way up on the soundboard. Um, so this could mean that science concepts and practices are being explored and aligned to grade level standards. So science is turned all the way up. Technology is both created and used purposely, so technology is turned all the way up. Engineering concepts and practices are being explored and utilized, so engineering is turned all the way up, or mathematics concepts and practices are being explored and aligned to grade level standards, showcasing math turned all the way up. So perhaps in a lesson in the unit, we can see all four of these disciplines turned all the way up. But we may also see in other lessons that the soundboard shifts a little bit in how STEM integration is approached. So here's an example where science is turned all the way up. However, technology and engineering are turned down a little and mathematics is turned off. This variation in STEM integration doesn't represent a gap. It really reflects what is most instructionally appropriate for that lesson. So the disciplines flex in the units depending on the goals of the lesson. And this really is connected to how real world STEM professionals work. On any given day, they can be engaged in various forms of STEM integration, where some of the disciplines are turned up, some are turned down, and some are turned off. So here's what it looks like in 8.2 from our perspective. Here are all the variations of STEM integration that students will experience in this unit, at least in the areas where computer science is integrated. So this kind of integration, we believe, allows students to experience computer science as that powerful tool for sense making, and computer science really becomes the amplifier for STEM integration for students in these units. One thing we wanted to note beyond our rationale for why we took on this approach to computer science integration in the units is that we believe the units can be used in a variety of ways. The first being, if you're already teaching OpenSciEd units, we believe that these units can replace those existing units. Again, the same standards alignment for science, and now we've added in computer science. So they can be replaced in your scope and sequence. However, if you are at a school or you're using another science program, we believe you could pick up one of these units and use it as a pilot effort to try out OpenSciEd. We also believe the units could be used in a middle school computer science class or in a middle school STEM or engineering class for the reasons that we saw just a moment ago, that these units really focus on STEM integration and bring in engineering and technology. However, if you're going to use them in a computer science class or a STEM or engineering class, we would just recommend that you work closely with the science teacher in your school to ensure that there is coherence and alignment with what they are teaching. All right, so that's a little bit about the overview and the rationale behind our effort to integrate computer science and science in these units. We're now going to turn our attention to really getting to know the 8.2 plus computer science unit of sound. And I think I'm turning this over to Nicole, is that right? All right.
Yes. Yeah. So within the OpenSciEd middle school scope and sequence, I just want to point out that the green units are the ones that are going to have the CS added to them. And we are going to focus today on the one that's circled in pink, which is 8.2 sound waves. So Tiffany, if you want to go to the next slide here. So notice that we are keeping the same performance expectations from NGSS, which on the next slide should have, or nope, we're going to go to, we'll look at them in a second here, but MSPS 4.1, 4.2, and then MSLS 1.8, which is about sensors and how we make sense of our world using our eyes and ears and nose, which is done over across numerous units within the middle school scope and sequence. So let's look at 8.2. So we have 13 lessons with an optional lesson 14 as students tried to figure out how can sound make something move and how we can produce and detect it. And this is set up for 22 days of instruction, working on a 45-minute class period. But if you choose to do lesson 14, which is optional, that's an extra 2 days. So total of 24 days of instruction. So let's take a closer look at our NGSS performance expectations. So we're really working on understanding waves and characteristics of waves. And so students get into wave models and we relate amplitude and energy of the waves. We look at how waves travel through different materials. And again, we think around our sensory systems and how we respond to stimuli. So let's see our CSTA standards. And so I'm going to go ahead and put in the chat the codes there that Tiffany showed us earlier. So we're getting into computing systems where we're looking at hardware and software and how those are combined together. We're working with data analysis and using tools, computational tools, and to gather our data, make it more reliable. Algorithms and programming, we're creating flowcharts, we're defining variables, and then on our next slide, we have some more algorithms and programming. Looking at procedures and thinking about how we can organize code and make it easier to use, and also documenting what different specific pieces in the code do to allow us to follow the code, share with others, test it, and debug it. And then we think about the impacts of coding and really thinking around who should have access to the information that we are gathering using these tools. Okay, so let's look a little bit at the technology that we are using in our unit. So our primary technology are microbits, which these are a small little computer. They are smaller than the size of a credit card. And so these are used across the units. They have an LED display, including your microprocessor. They also have a lot of internal sensors that we leverage within here, and they are interactive. So you can push buttons to make them do things. And the logo, which is right above the LED display, is also touch sensitive that students can use to program it to do lots of cool different things. So what programming, so the sensors that we're using in here is the light sensor, and then also the tilt sensor. And then we have various different outputs that students are able to gather data from. So including the LED display, we use the radio function of the microbits, which allows them to talk to each other. That works on Wi-Fi. We also have them connect directly into the computer to provide data outputs using the serial write or the USB ports and that built-in speaker because of sound. But sometimes those sounds on those built-in speakers are a little limiting. So we also include some amplified speakers to allow us to do some really interesting thinking around technology, which Michael will get into when we look at our lessons in a little bit more depth later. So how do we get these things to work? So we use a program platform called MakeCode, which is used across all of the units. It is an open source program. By default, it does use block coding, but it does also allow for students to switch between block and script coding. Okay. So as we talked about earlier, the CS integrated units maintain our instructional model within that. And again, we also start with our anchoring phenomenon for each of them. So we're going to explore the storyline of the 8.2 computer science unit. And as we go through this a little bit as students, channeling our inner eighth graders and a little bit as adults, if you're familiar, you'll be able to notice those similarities and some of the differences. So Tiffany, if you want to go to our next slide. So we're going to preview and remind ourselves a little bit of lesson 1. We'll engage in some student hat experiences in that lesson. And then we'll talk through lesson 2. We'll spend a little bit of extra time in lesson 3 doing some student hat experiences and also getting into lesson 4 around the CS. We'll do more student hat in lesson 10 and again highlight some of the changes in lessons 7 and 11 where we're looking at how we're integrating computer science into the unit. Okay, so I'm going to pass it off to Michael to get us started with a little bit more in-depth thinking around our first lesson set, lessons 1 through 6.
Yeah, and I think then I'll pass it back to you by the time we hit lesson 3, right, Nicole? So let's get ready to get oriented to the very first lesson of the unit, lesson 1. If you would, Tiffany, move us to our next slide. I'll give you a teacher overview first before I ask you to jump into some student hat thinking. And the gist of this lesson is a 3-day lesson where we engage in the same routine we use at the start of every OpenSciEd unit, the anchoring phenomena routine. Goal to generate lots of questions that come out of a common phenomena we observe. And that phenomena is we're going to see that when loud music is played from a truck in a parking lot, a window on a building across the parking lot is going to visibly start moving. And then we're also going to see that, when we try to recreate some of that system, like a speaker and something that represents a window in the classroom, we actually can get like this plastic wrap over a nearby bowl to also like visibly move when music is played from the same song. So let's see what that looks like kind of from the student's perspective. We say that's what the phenomena sort is that we engage with, but let's engage with it as students would. So let's put those 8th grade hats on and do some modifications for Zoom rather than do the discussion we might have in the classroom. So get ready to put things in the chat. So welcome 8th grade students. I'd like to introduce a phenomena for you. Let's check this out. Yeah, in the chat, I just want you to share something you notice or wonder as you watch this video of this thing that happened.
Just on the side. I work with these guys. Yeah.
We'll do only one pass on that, but it's maybe something stuck with you in terms of a notice or wondering you can add to the chat. We'll give ourselves 30 seconds just see what pops up. And Nicole, if you start to see things start coming into the chat, maybe you can elevate a few of the comments.
Okay, so Amanda says that the gentleman's shirt shakes and the window across the parking lot moves. Nicole says the car is not touching the window, but it's shaking.
About 5 more seconds, see if we get any wonderings that start to come up. Cool. Got a little bit of a taste of sort of the intro to the phenomena that kids experience in the classroom, starting to raise some noticings. And it's kind of like that Nicole's point there is like with the exclamation point, kind of strange, like there's no contact, right, in between the two things. So we'll advance to our next slide and start thinking then about like that piece that Nicole's sort of talking about. There is clearly a place where the sound's coming from, somewhere in the truck, right, and the window, but there's the in between. There's no touching, right? So what I want you to think about, like, what would it, some different ideas you'd anticipate a student saying across a whole class of students, right? Because anticipate them coming up with if they were asked to model a response to this question. Why would a sound coming from one thing make another thing far away move to the point also when they're not touching? So think about what my kids say. And I'm actually going to zoom into this a little bit more, Nicole, to kind of emphasize that if we had more time, we'd fill this out ourselves. But could you advance one slide, Tiffany? So imagine we're asking kids to kind of zoom in on the spot where the sound's coming from, like a speaker, zoom in on the window on the other side. But of course, really mysterious is like, what about in between, in the space in between? So think to yourself and then give yourself like 30 seconds and like just, blast of bullets. Kids might say this, and let's see what some ideas you would anticipate them coming up with. Amanda, I think you spoke to having taught the unit before. So you're saying, we're going to hear waves, but you push on that or ask them like how they represent, you're going to like, I don't know. I just know that's the right answer. Okay. Thanks for sharing that. And Roz, you're saying that vibrations somewhere in the system. Love it, Nicole. Like wind, like kind of blowing across right from one place to another, making it stuff shake around like leaves on a tree. Cool. Wait for a couple more in case they come up. And Nicole, Tiffany, make sure like if you're ready, give me a thumbs up. If you're like screen share, it's okay now. Cool. So we got maybe 3 different ideas out there. And of course, given more time to kind of compare our ideas with others, it might raise new insights that we hadn't considered before. And what would we next do as a class after we've individually modeled and started sharing our models with others? We're going to do what's on the next slide. We're going to say, all right, just like in every OpenSciEd unit, we're going to gather in a scientist circle and get all of our resources on the table. What are we thinking? Let's make a group record. Everything we agree on. Do we all agree on wind? Do we all agree on vibrations? Do we all agree on waves? What do we even mean by any of these? And maybe we got competing ideas. And then to the third bullet, as we talk, new ideas might emerge that we hadn't considered until we heard each other's ideas. We won't reenact that entire moment in the classroom where we would build that artifact together, but we thought we'd show one. What's kind of artifacts we tend to come up with. Same as in the original non-CS version of the unit. And not much here has changed, except for some tightening up of how to build maybe the amplified speaker system there at the beginning. Some directions on that. Can you go to our next slide? And we'll just take a look at a sample. Amanda, you can give us a thumbs up, maybe a thumbs down, or others can also sort of say the same. Is this kind of look at the kind of things you do here? Like kids are going to say, I don't know, waves, maybe it's particles, vibrations. Or maybe it's even different for like the boom sounds. I don't know if how often that comes up. Like not the whole sound is making the window shake. The whole sound, only parts of it. Right. And then what do we mean by waves? Like water waves, particles spreading out, sound particles. And then what happens on the other side, right? All the things that have question marks represent, we're not sure. That sounds maybe like a reasonable possibility, but it also might be different than a different idea we're hearing from someone else. But we do agree on a sound source, a sound receiver, and sound somehow traveling. The next move we make in our anchoring phenomenon, I'd like you to also consider in student hat. Let's go ahead one, Tiffany, and just kind of stop and jot for yourself, particularly if you're new to this routine. Where else have you seen something or experienced something like this? Any experiences related to what we've observed so far? It could be like sound causes stuff to shake, or just sounds being made and something making those sounds, or something receiving the sounds, like the window. Or you've just experienced something over distance. So we're trying to just kind of broaden as much as possible. So I take 30 seconds to just jot down maybe a bolded list of things that come to mind. Cool. And I saw Nicole throw into the chat, and if you've been writing on paper, maybe you can compare what we're coming up with and see if your ideas are reflected on this example we have on the next slide. That's from typically classrooms come up with like, oh, it's a group of 30, lots of things. Oh, and they're sure, look at that thunder one is there, the third bullet. But maybe you can also write down for the rest of us, besides Nicole, who didn't get a chance to put it in the chat, just give us a thumbs up if you're like, oh, I see my idea here. And a thumbs down if, nope, I got something new. Seeing some thumbs. Roz and Christy got the thumbs up. All right. Getting some representation. Love it. Cool. And we'll go on to our next slide because when we kind of pivot to related phenomena, it sort of then seems like a prime moment to be like, wait, so what questions do we have? And about what? About anything, any of the phenomena we looked at, whether it's the initial one we started with, all those related one, the model we tried to make to explain the initial phenomena, class consensus model. So maybe this is another opportunity for you to kind of think of like two questions, just what you are now wondering based on what we've observed so far, like channel what a student might wonder, or maybe you're like, I'm in my adult hat, really. I mean, I'm wondering this myself. Put two of those in chat and we'll see some kind of the questions that tend to form at the end of this first lesson from students. Cool. Give an opportunity for maybe another 10 seconds. I see a couple from Roz and Nicole there. We'll elevate, but any others want to add to the chat? That'd be lovely. Cool. So we've got some questions about about how the glass is responding and breaking or not breaking, if it was made of something different. And then Nicole asking, well, what even is sound made of? And then is there like damage associated with or some hurting to happen to the person's ears that is in the car, or maybe even behind the window? I'm not sure which other possibilities might come up in students' questions, but we've got at least got those two there. And that's kind of the goal of our anchoring phenomena routine, is start to raise questions that students really want to figure out, whether it's about how we hear, could there be damage, what is sound made of, different materials. We want to honor all those questions and try to answer them in the arc of the unit. And so the order of lessons that we follow tries to follow also students' ideas for investigations, the questions that they come up with, and we're going to overview that in subsequent slides, but gave you a little bit of a taste of how we're going to end the anchor, which if you've taught the sound unit before, be like, this feels very similar, right? Okay, let's move ahead to our next slide. So now we're going to switch back to teacher hat. A little bit of whiplash here. Anytime you see those red slides, which will next happen in lesson 3, we're going to go back to Nicole and she's going to take us into student hat. But let me do a little teacher hat orientation. Lesson 2 is much like the old lesson 2 of the prior version of the sound unit. So what's up with the sound source? What's happening when a speaker is making sounds or other sound makers? So we're going to go touch and explore some musical instruments and speakers, and then we're going to watch them too in slow motion to try to get a sense of what exactly is happening. Largely the same as before. With this third lesson, though, the little CS icon, I'm clued in that, Nicole, I'm passing it back to you because things are starting to change now in this version of the unit.
Yes, so we start to think about like what's happening between the consensus model that we had, that big question of what's happening between where the sound is being produced by the speaker to where the sound is making like the window shake or our ears hitting our ears and we can hear it. So we start to think about what's happening as the sound is moving through different matter. So Tiffany, let's look at the next slide there. So they carry out this sound movement investigation. So students work together to develop an investigation plan. This is where we first start to look at code. And I know the images on this slide right now are small, but when we engage in Student Hat, we'll have a chance to look and engage with how students are looking at code for the first time in this unit. Students look at two different codes. They activate microbits inside a sealed container. And so the video that we're going to watch here real quickly is going to show a couple of those sample investigations that students can carry out. Okay.
And since my heater came on.
Wait, Nicole, is that underwater?
It sure is.
Okay, large jar, no vacuum seal, submerged.
So in these investigations, students are thinking about like, I've had my head underwater and I've heard sound. So we think about sound traveling through water and light, traveling through water, traveling through air, traveling through the solids of the jar. So if you noticed, you heard the word vacuum. So we try to like isolate and remove each of the different types of materials that the sound can travel through. So let's go to our next slide and experience just a little early part, kind of halfway through day one of this 2-day lesson. All right, so channel your inner 8th graders. So in your groups, you're going to get to select code that you are going to use to activate the microbits once we put them inside these sealed jars. So one of the codes is going to activate using a flashlight with light, and another one is going to use the radio and buttons. So as we look at this light activated sound source code, I want you to think about what are the inputs that are going to activate the code, so cause it to change, and what are some of the outputs that are produced. So Tiffany, if you want to go ahead and show our next slide. So let's just kind of orient a little bit to our code. So this is our block code program. And where I want you to kind of look is at the forever box. You see there's the blue on start and then the blue forever. So as you're looking and engaging and thinking about what are the inputs that are going to activate the different outputs and what are the different outputs that we see. So I'll give you about, what do we think? 30 seconds or so to put in the chat either an input that's going to activate the code and cause an output, or what are some of the outputs that you see? All right. So yeah, Amanda points out that the input is the light level. So we can see that kind of in that pink purple color. And the outputs are the LED displays. So those are the smiley face, sad face, get your umbrella out because it's really, really, really bright, or different sounds, which are in the red blocks. So students have more than 30 seconds to look at this and determine like, what are some things that maybe we need to change? And that's a good question, Amanda, where the happy and the soaring, those are preloaded. And that's one of the considerations that students think about. If everybody's playing the same sound in the classroom, how are we going to be able to tell our data apart? as we're carrying out our investigation. So students have a chance to also brainstorm some potential changes that they would make to the codes for the light activated or the radio and button activated sound sources. So that kind of wraps up day one. And let's look at, Tiffany, the next slide of how students go into this. So they first test their code in MakeCode. There's a virtual interface that is really great that allows you to interact and test the code to see if it works before you even load it onto the microbits. So the radio and button activated code, they can virtually move their mouse over to the A and B buttons on the virtual microbits. And once they add in the receiver, they get 2 microbits, because with the radio codes, we're talking kind of like a walkie-talkie back and forth with each other on a channel. And then for the light activated code, there's a little sensor that acts as the light sensor that is embedded in the microbit, that they can change the amounts of light shining on the microbit. To not only kind of test some of the ranges that they see, but also test how it's changing the output. So that smiley face, sad face, and umbrella. So let's go to the next slide. So students modify, they test their codes, they get the base codes that they spent some time looking at with paper first, and they test all of those different changes in the virtual interface and getting ready to move forward with testing on day 2. Yes. All right. Thank you, Michael. All right. So let's see where we go from here in lesson 3. So in lesson 4, we think about how sound is traveling through matter. So at the end of lesson 3, we figure out that sound requires a medium. They watch a video of a much stronger vacuum that reduces the amount of air in a bell jar to where I can see a change on the LEDs, either using the light activation or the radio button activation, but I can't hear anything anymore. So we know that that sound needs matter to travel through. So now we're wondering, like, we have this idea about a wave, but the wave is interacting with the air particles or solid or liquid particles. So exactly what's happening here. So we go into a simulation, and we use our bodies to help look at that simulation of how sound waves are traveling through particles. And we start to really build out that compressional wave understanding in lesson 4. And then lesson 5 is our first time getting into our senses and our ears. And so students start to think using computer science input-output models for sensor systems, but we're applying it to our ears and how we hear. What's the input and what's the output? And so we carry out the salt on a drum, or in this instance, on top of a bowl, to think about how sounds cause the vibration, and we use the salt to help us see the different vibrations happening in there. So here we're doing computer science thinking without engaging with any technology or microbits by applying an input-output model.
Ooh,
And then
noticing our text is off on that.
Yes,
Nicole.
I know. I noticed that too.
Clean that up.
That very well. And then Tiffany, if you want to go to the final lesson in our first lesson set, here we go back to our driving question board and we start to think about, like, how is the sound making that window vibrate? Like, it is far away, something's happening. And to kind of go back to our question, like, well, did that hurt their ears? Like, what do we do when we're around loud noises to protect our ears? So students take a transfer test to look at 2 different prototype hearing protective devices that incorporate a vacuum. And I think I'm passing it back to Michael to talk us through our second lesson set. Oh, you're muted.
Well, thanks, Nicole. And it's interesting because if you think about the reordering of lessons from the old sound unit, it's really at the end of lesson 6, we have an answer to the anchor. Like we could be done with our driving question board for a large part, but there's a problematizing move we're going to make to set up lesson set 2, which is not all parts of that song made that window shake. What was it about those parts of the song? Help kids raise, is it about loudness? Is it about bass? What does that even mean? Like, what is different in terms of the vibration? So, the characteristics of sort of like what might be different about particular sounds is going to be the focus of lesson set 2. But we have a model going in lesson set 2 that takes us from the sound source through the matter to a sound detector that we're going to hang everything else on. So let's take a look at the lessons in lesson set 2. Lesson set 2 starts with considering, well, what's different about louder versus quieter sounds. And so a kind of an overview of what we do in this lesson is we're going to use a large wooden or metal stick to kind of explore what happens when you hit it harder or softer, just like we have seen with the instruments like the drum or the xylophone or the tuning fork, and then try to like get a sense of like what's different about its vibrations. We're also then going to explore what's different about the vibrations of a speaker too, and get some data that allows us to compare the graphs of those vibrations over time. So a bunch of graphs are produced, and I want to now kind of get a little bit more into the details of the CS use here, because I can see a little icon up top there, because this may look similar to like what kids did in the other version of the unit, though it was as a teacher demo. Here's what kids are going to do. Let's go to our next slide. Every group is going to work with a tilt sensor on the end of a stick and set it in motion and collect data from it, and then learn how to transform that data and graph that data and look for patterns. So for example, here's a Google spreadsheet down below that kind of gives a sense of the data kids would analyze that they gather themselves from like a soft push versus a hard push, trying to mimic a more forceful strike or pluck that like on an instrument, but they're collecting that data themselves and seeing some patterns there. You may already start to recognize some. Amanda, I saw a wave of a hand, but that might have been to a colleague though.
Is it okay if I ask a question? Is this graph and data cleaner? Like I've been doing this, I have every student group set up with Vernier probes. And it works, but the little lab pros adjust the scale on the axis, so it's really hard for them to see the difference in amplitude or frequency. So is this cleaner for them to compare?
Yeah, we think we got that taken care of.
Okay, awesome. Thank you.
And got it in their hands because veneer was great, but it was super expensive and noisy. And I should say, coming in, we do consider all the possible sensors we could use based on our work from 8.1 and agree like, oh, we could probably hook up any of these to this thing. There might be issues with how clean that data is that we've taken care of on the back end, but we do get kids' wheels turning in their heads. They're like, oh, there's a bunch of sensors we already know of that could serve this purpose. This tilt one, though, is clean, and that is real data. And down to a very small, like 1-inch deformation, you'll get good, clean data off this thing. Cool. So let's move beyond lesson 7 and go to lesson 8. Lesson 8 also mirrors something that was in the old unit, but it's at a different position. And that is the idea of like, well, okay, we figured out loud versus softer sounds, but what about higher versus lower pitch? And we simulate something that we do with a coffee stir, which is we pluck it at different lengths and notice that it's making different pitch sounds, just like a xylophone, just like some of us say happens with guitar strings when we lengthen where we're putting our fingers on them. And we put microbits on the end of those and collect data from those. This is a short lesson, though, of a single day. We do give an option that you could have kids collect all the data from soup to nuts, but here we kind of do a little bit of demonstration of the sticks. I want to show that on the next slide, and then just look at the data that's produced by them so that we can get into some coding. So let's, maybe if you wouldn't mind, Tiffany, press the video. You actually set these up in class. Just gives kids a sense of like what might be different between them. It already gives us probably an intuition of like, oh, I already kind of expect what the graphs might look like for the two, or something that might be different about them. They're down below there. But then we get into the second half of that day to be like, It would be so nice if these things automatically calculated one of the things we're seeing in the graphs, which is this like how often the waves are repeating in a certain amount of time or frequency, rather than us having to do it by hand. So we describe what that algorithm is. We look for functions in the code that might help us do it. We discover there actually is some code in there that looks like it's doing the calculation. It's just very obscure. So down below, there was this output of this scrolling number, and we're like, oh, I guess it's actually auto-calculating frequency, but we could totally make that more clear to the user. Let's start recoding this thing and test it again and see if it actually can get what we think its frequency is. Download it, and we do that as a class. We do a little code modification, put it on the microbit, and run it again. That's the end of lesson 8. We'll move on now to lesson 9. Lesson 9, much like the old unit, in that we use a simulation to try to explore what exactly then changes in the medium when we change the amplitude or the frequency of the sounds being produced, or we know now these have to do with loudness and pitch. But we use a second simulation from some friends at, you have to remind me where at, Nicole, again? UC Davis, is that right?
Yeah, it's UC Davis.
Gave us a second simulation that we think kind of strengthens the unit and helps us dig into some other ideas like changes in pressure and changes in density more clearly. But from those two, we figure out what's happening to the particles in the medium. We represent those as graphs as well. Lesson 10 then moves us to the question, okay, if we have now figured out pitch and amplitude are ways that we can change the sound of the sound source, then like, can we make any sound by just changing those two things? It'd be cool if we could like synthesize that. So let's do that. Let's see if we can like reprogram a computer to synthesize different sounds. So we open up a microbit-based piece of software that's loaded on the microbit. We don't have microbits for you to use today, but in a moment, I'm going to engage you in Student Hat with a virtual microbit to try some things. So let's go to our next slide and welcome you back as 8th grade students. So here we go. There is a URL. If you have a browser open, you could open this. And then you'll get a loaded diagram in the left corner that looks like a virtual microbit. I'm going to give you about a minute once it loads to do this. Press button A a couple times. Make sure your speaker's turned up so you can hear it. Press B a couple times, and then press the logo a couple times and kind of record what you notice is happening for the sounds that are produced. Or make note of what's happening. We won't take time to record. If you had a chance to test it, you'll notice A and B keep producing the same sort of thing, and C, or the press the logo, gives a little more variation in what's happening each time you press it. So let's go into our next slide in Student Hat. And then do the same thing that we'd ask kids to do. You know what? Take a moment, look at the code here. We pass a reference out, but we'll have you do it based on what's on the screen. It's also on your computer right now if you've loaded the code. And think about like, wait, what piece was making the sound that I heard? And what kind of changes might I want to try if I think I know what that does? Amanda, looks like you have a question. Okay. Okay, we'll go on to our next slide. After we brainstorm, then we're like, well, clearly we want to try some of this now that we think we might know what these pieces of code do. So we have kids access the same code, but now press edit, which you can do as well. If you want to take maybe 30 seconds to try that, try making a modification to the code and then test it in your virtual interface by pressing the A or B buttons or the logo, depending on what part of the code you're modifying. And if I could grant you 10 minutes to keep messing around with variables and values and a whole bunch of good stuff, I would. But I'm going to move us ahead to the next experience that we give students, which is, and I'll ask you guys the same. Yeah, how many of you have used another, I'm just curious, how many of you have used another programming language other than these blocks that we've been using? And you can channel what you think your kids would say. Would they have some yes, no? And throw that in the chat. Oh, sorry. Got a thumbs up from Nicole, who I think was at one time a CS novice, but is now like, I think I have. Little did I know that I've used other languages. Raz is just like, yeah, cool, cool. Well, students, many of us might have those experiences, but maybe not all of us do. I mean, Lisa says she has also, but I want to give you guys an opportunity to experience other languages too, because if you're interested in high school, maybe in pursuing something with computer science, might be nice to know like what that looks like. And so let's take a little dabble into some of these other languages. Here's actually three total languages that are used in that interface, not just the block-based ones, the make code ones, but there's also script-based ones, JavaScript and Python. And so we would ask kids to, in a moment, take out their colored pencils, identify corresponding parts or blocks in the script-based language and describe what they do. We're going to ask you to do a little shortened activity showing you the kind of handout we give kids to support this type of thinking. If you could go ahead to the next slide, Tiffany. Well, looks overwhelming at first, but all we ask you to do right here now is, hey, what lines of code in the JavaScript on the left does the block code in the purple box correspond to? And how do you know? So you might give yourself 30 seconds and then we'll see if we get some ideas in the chat. And you can refer to lines of code by number on the left side. In the interest of time, we'll pause there, but this is just sort of our first experience, which is actually at the end of our 5-unit sequence of CS infused units, where we're giving kids a chance to like start playing with and modifying script-based code. So you gotta toe in the water before they go to high school, because like many high school classes, this is the kind of code you'd use. Am I interested or not? I have to kind of know what that looks like, right? And so giving them a little under the hood here for script-based code is this experience we do in this lesson. And it's not the only thing we do in the lesson, but I will pause there and then move on to our last couple lessons, and we'll skip that one for now, if that's okay. And pop back to teacher hat. Everything else here forward is teacher hat, and we'll go kind of fast here, so we still have a little time for Q&A. But lesson 11 has us look back at the anchor one more time, because it turns out that if we watch that video, the guy in the video like did something in the middle that changed the music. In fact, he left a lot of text at the front of the video that gives us clues about things like subwoofers and amplifiers that maybe we didn't know what they were, but in this lesson, we're going to figure that out. And we're going to realize that, you know what? He actually probably had something called a crossover in his truck that sent certain sounds to the subwoofer and certain sounds to his tweeters. And we're going to start with the program that we used last time and build a crossover out of it and use it to explain the anchoring phenomena, because we actually think this actually maybe also was happening in the anchor, and we can better explain how and why that would have caused the window to shake. So here's the moment where we put pieces together and marks the end of lesson set 2. The first part of that 2-day lesson is some tinkering with code, but in service of like, let's fully explain the anchor by trying to recreate the system we think that's at play in the truck. With that, I believe, Nicole, I kick it back to you for lesson. So sorry, I missed an opportunity to briefly mention that means we're building an amplified speaker. We're changing up the code. There'll be 2 speakers in our system. We'll build a flow chart to kind of figure out the logic, and then we turn it over to kids and be like, yeah, build it and test it and see if you can get it working. And then, Nicole, I'll kick it back to you for our last lesson set, 3 lessons.
Yeah. So lesson 12 is our second experience going back into hearing. And so we've spent some time looking at how technology and hardware can be used to create sounds of different pitch and move them around so that different speakers play different pitch sounds. But like, how do our ears do that? So we zoom into the structures of the ear that we first started to experience in lesson 5, and we figure out that when we are exposed to loud sounds, or just as we age, the structures inside of our ear change and they can become damaged to the point where we start to lose our ability to hear higher pitched sounds as we age. So we take that and we move into lesson 13, which has 2 different pathways depending on how kids want to move forward with the unit. So we close out the driving question board, and then we take a poll on how do we want to end the unit. Are we interested in thinking about animals? Like, we've got technology, we've got humans, like, what about animals? And so if students want to continue on and they show interest, then we move to 14. If not, we stick with lesson 13 and we totally close out our unit. Students complete a transfer task thinking about mosquito tones, which are very, very high-pitched tones that young people can hear and adults cannot. And they were originally used to keep teenagers away from storefronts. Like, stores would play these high-pitched tones that would like make teens' ears hurt, and so they would move away. But then teenagers flipped the script and used those to be able to communicate with each other with sending sound notifications that adults could not hear. And so if students want to look at animals at the end of lesson 13, they have an option to read about how 10 different animals here, and then we move into lesson 14. Where we think around like, how can we study how animals interact with sounds and sound in the environment? And they are introduced to bioacoustics. And there are 3 different readings around different types of ways of bioacoustics are used to help us think about animal communication and communicating with animals and how sound impacts animals. And so we start to think around who should have access to some of that information, how safe it is for the animal, for people to know where the animals, how they're migrating and how they're moving through the world. Regardless whether kids want to end the unit at 13 or 14, we wrap up with a reading around hearing aids and how the development of hearing aids really integrates life science, physical science, and computer science thinking, as well as technology and engineering. And that wraps up our sound unit. So I think I'm handing it back to Tiffany.
Yes, so thank you all so very much. We're gonna just give a few little final um, uh, bits of information to you, and then we'll open it up for questions. So our computer science integrated units, we have 2 units published now, units 8.1 and 8.2 plus computer science. But we will have our remaining 3 units published sometime in the winter of 2025, maybe winter of 2026, meaning early January. We'll see how it goes. But we also wanted to quickly share specifically some new support features we've embedded in the computer science units that we think will be very helpful to you if you're implementing them. So Nicole, I think you're going to share a few insights into these support materials.
Sure. So I do want to say these materials came out of our work with our field test teachers and the need to better support them with working with the microbit technology. So every unit has a summary of microbit activity resources that is found in the first lesson. And then to help support both teachers and students in using and designing the different investigations, we've created reference slides that have embedded videos of how to put things together and how to run the code that are both student and teacher facing.
Wonderful. And for those of you who are familiar, these other materials will not be new to you, but if you're new to OpenSciEd, we also have for every lesson in the unit a teacher guide, as well as slide decks that are student facing for each lesson. We have a wonderful comprehensive teacher handbook, which will give you insights into all of the instructional model of OpenSciEd. We do have student editions. I'm not sure why the image isn't showing up here, but we do have student editions, so student sort of facing materials that you can pick up and use. We also have available kit lists for every unit that you can source yourself, or we have the ability for you to connect with some of our certified kit vendor partners who can also provide materials, as well as simulations of videos, all free and openly available to you. We also will have printed materials of the CS units available on our website. They're not there yet, as well as certified kit versions. And so we're working with our kit vendors to make their materials available as well. If you want to find out more information when those print materials are ready and the kit vendors are able to provide those materials, you can check out the link here. Actually, I believe some of our certified kit providers already have materials available, so I misspoke a moment ago. Some do and some don't, so you'll just have to check with them. And then we have a slew of other resources you can access through the slide deck that we've shared in the chat. Well, you can always reach out or contact us with further questions through the OpenSciEd website. We also wanted to let you know that there are some other webinars coming up, not necessarily related to the computer science units, because remember, we have 3 more that we're working on right now to publish sometime in the winter. But we do have a couple of other exciting webinars that you may be interested in. So we have a new set of professional learning resources that are available through what we're calling our on-demand teacher support library. So if you've been teaching OpenSciEd for a while or you're new to OpenSciEd, this is the space to find out more about really teacher-centered professional learning supports that were developed with and by teachers using OpenSciEd. And then if you're interested in thinking about AI and in the OpenSciEd space, then August 28th might be the webinar for you, and you can register here in the links are in the slide deck that we provided, or you can go to the OpenSciEd website and register. We just want to thank you all for joining us today. On behalf of Michael, Nicole, and myself, we've had a great time with you, and thank you for engaging with us in both student and teacher hat today. And let us know how it goes if you're implementing the units or if you need support. So we appreciate your time today and enjoy the start of your school year.